Next up, we have Nati Srebro, also known as Blake Woodworth. Sorry.
Yeah, I'm not Blake, but he is here. Right. Okay. So I'm going to discuss an open problem regarding memory-constrained optimization. And I've been talking, you might have heard this before, I've been talking about this problem for several years now. In the last few years, there's been some work on memory, significant progress on memory-constrained learning. And I thought it's a good idea to bring this back up. And I mean, we have no idea how to solve it, but maybe you do. Okay, so the problem we're dealing with is just want to optimize a convex function and for simplicity take what I consider the kind of simplest optimization setting, convex Lipschitz function over a bounded domain using an exact first order oracle. So there's nothing stochastic here. So, and what we're going to be looking at is how many queries to the function, how many gradient evaluations do we need in order to optimize. And we all know that the best we can do here is d log 1 over epsilon queries. This is in infinite dimensions. And this is attained by for example, by the center of mass algorithm. How many people actually here use the center of mass algorithm on a daily basis? Nobody? Okay. You might, though, use gradient descent on a daily basis. Okay, so we don't actually use center of mass to optimize. We typically use things much more similar to gradient descent. And this has, in some sense, much worse query complexity. I mean, it requires 1 over epsilon squared queries instead of a logarithmic number of queries. And the reason we use gradient descent, not center of mass, is for many reasons. I mean, center of mass as is kind of unimplementable. It's very complicated. There are methods that still have log 1 over epsilon complexity or poly d log 1 over epsilon complexity and are implementable, ellipsoid or various approximate center of mass using various sampling techniques. How many people use those on a daily basis? Still nobody? I mean, here I expected maybe one. I mean, and so, I mean, even those are very complicated. And so what we want to capture is kind of, is there a simple algorithm that actually attains this d log 1 over epsilon query complexity, or at least something better than 1 over epsilon squared? In one way, I think, to separate between them, so we can talk about runtime, but runtime, we have no idea how to give runtime lower bounds. Instead, we can look at the memory lower bound. So for center of mass and all of these other algorithms, all of them require quadratic memory, d squared memory. You have to store all the gradients so far or store some ellipsoid. All of them require d squared memory. And so with gradient descent, one way to think about it simple, it also is linear time per operation. It's also linear memory. Okay? And so really you can think about separating them in terms of memory. So if you look at this memory and query complexity trade-off, there are two different points here. Center of mass is optimal query complexity, but very high memory. Gradient descent has optimal memory. You can fairly easily prove this is the optimal memory you need, but very high query complexity. Okay? And as far as I know, these are basically the only 2 points we know. So we know that everything, we have these two lower bounds, all this red region is unattainable. The green region here is attainable, basically either by gradient descent or center of mass. And the big square in the middle is completely unknown territory. Okay, so what we'd like to understand is really, can we go into this rectangle? On one hand, it is possible, and it would not contradict anything I know at least, that there's an optimal algorithm that uses the d log 1 over epsilon queries and only d log 1 over epsilon memory. On the other hand, it might be that this, so meaning this entire square is green. It's also possible the entire square is red, right? That you cannot, there's no trade-off possible here. You have to just choose one of the extremes or anything else in between, right? So we might have a trade-off. So for example, it might be interesting to devise, if I tell you that you can use, instead of d memory, you can use d to the 1.5 memory. Can you improve over gradient descent somehow? I don't know. Okay, I'm not even sure what I would do in that case. And so the main open problem here is just characterize this entire trade-off. Tell me exactly what's attainable and what's not attainable in this big question mark. Exact characterization of the query complexity within the function of memory bounds and bits. And for that, you'll get a dinner, but not a dinner in Google with all due respect. You'll get a 2-star Michelin restaurant dinner, agreed upon place, or there's an alternative cash prize. You can see the cash prize is detailed in the write-up. If you can't get a full description, there's some intermediate points that, that could still be interesting. So in particular, if we want to really stick to roughly linear memory, so not do something much more complicated than gradient descent, is there any way to kind of avoid that poly 1 over epsilon dependence? Can we get something that only depends this is, it should say polynomial in D. Okay, what we want here, despite what it says correctly, is we want something polynomial in D and logarithmic in 1 over epsilon. So maybe not d log 1 over epsilon, but d squared log 1 over epsilon, or d to the fourth 1 over epsilon. And again, this would get you a 1-star Michelin dinner. Alternatively, can you get something which looks almost optimal, so it's just only a linear in d query complexity, but that beats this quadratic memory by even a tiny bit. So it has d to the 2 minus delta for any positive delta memory. So can you get optimal query complexity or near optimal query complexity with subquadratic memory? Okay? And finally, if you want to settle for a Michelin Bib Gourmand restaurant, there's some very nice Bib Gourmand restaurants in Chicago. This is not so bad deal. Basically, any polynomial intrusion into this question mark will earn you that. So anything, either a method that shows any type of trade-off between those two extremes, or a lower bound that tells us we cannot get to this bottom left-hand corner. And I want to, actually, how many more minutes do I have? 1 minute? Okay, so just one reason this is a bit trickier than the memory lower bounds for learning is that this is an interactive process. So in learning is a non-interactive process. You just sit back and collect examples. And so you can, so if there's no, the examples you get them, just the query don't affect what you make in the future. Whereas optimization is an adaptive process. I mean, you query points based on the answers you got in the past. And this makes it kind of much harder to study definitely, if you want to reduce things to communication complexity, it doesn't seem possible because of this interaction, and it generally seems much harder to get memory lower bounds in these interactive processes. Okay, that's all. Other questions? I don't think you can. As far as I know, you cannot improve over the d squared memory by sketching. I'm not sure. Yeah. That's a good question. You can always take the cash alternative, but the dinner will be discussed. The terms of the dinner will be discussed. What? Solve the problem, and then there's a cash alternative. You can just take the cash and discuss it. We can figure it out.
Let's thank So I noticed he